Yeah, and I'll just quickly mention, if you have questions, you can put those in the chat, or feel free to raise a hand or speak up during the talk so we can get your questions answered.
Yeah, so the way that I like to approach this talk in general is just to be pretty casual about it. So I feel like if we were just sort of chatting over a cup of coffee, we can talk about multi-level mediation for implementation science. So feel free to interrupt me as I go. If you want, you can raise your hand either by clicking one of the icons that allows you to show that emoticon. I can see that you're raising your hand, or you can also just drop it in the chat. Let me just make sure I have the chat up in case someone wants to add that info there. I always like to say, if you don't mind turning camera on, it's always nice to see everybody. But at the same time, if you don't want to, that's totally okay too. There are many reasons why you might want to share your screen, and that's also okay. Just want to check in. Can you see the slides okay? Maybe like head nods or some thumbs up. All right, looks good to go. So I guess, and also thank you, Greg, for the very nice introduction. I really appreciate that. Today I'm going to talk about, some multi-level mediation. I've never given a talk on multi-level mediation before, at least not to like a sort of a larger group like this. So I think one of the challenges I had to face was how to present this in an hour long or less, and really hit the concepts that I think are the most important, recognizing that this could easily be a full semester long or year long course on the topic. So I'm gonna assume that you know just a little bit. So I'm gonna assume you know structural equation modeling, and you've maybe heard of some multi-level modeling before. And so I'm going to talk a little bit about mediation. I'm going to talk a little bit about multi-level models, and then I'll try to bring it all together in multi-level mediation. And I think by the time I get through mediation and multi-level models, hopefully it'll be kind of obvious what multi-level mediation is and how we're going to use it. Yeah. So feel free to stop me if you have questions along the way. Happy to answer anything. Again, more of an informal setting. If some of this stuff is too basic, like mediation and MLM, it's just a little too basic, I apologize. Just taking my best shot at where I think you're at, and then we'll move through from there. So I'll introduce an empirical example that we sort of worked with throughout developing this talk. I just used some basic variables that I think are of interest to implementation science researchers, and it will help me sort of highlight the most important features of the examples that I want to talk about. And then I'll briefly review mediation. I'll briefly review multi-level modeling. I'm going to spend a good bit of time talking about centering. Centering is actually really important for multi-level models. And as a consequence, it's also really important for multi-level mediation. So I think these are sort of the three foundational pieces that are sort of needed to talk about multi-level mediation. So once we have those in mind, we can combine mediation and multi-level modeling to get to multi-level mediation. I'm just going to go through one basic example of it. I'm going to try to keep it as simple and straightforward as possible, but I'll highlight some of the alternative models that can be explored, right? So if we think of multi-level mediation as a family of models that could be used, there are several of them out there. I'll briefly talk about what those look like and what types of hypotheses that those could test, as well as some extensions that could be used for sort of further analyses to follow up. And then at the end, I'm going to talk about Bayesian estimation, and why it's basically, in my mind, essential for multi-level mediation. And what I'll give you a little bit of a clue in right now is that I don't think you have to buy into the philosophy which underlies Bayesian estimation. I think you should just buy into the fact that it's a tool in your statistical toolkit. And for these really complex models, they will probably run with Bayesian estimation, and they probably will not with regular maximum likelihood. And we can talk about why. All right, so we have a lot to talk about. Let's see how far we can get in the next 40 minutes or so. So the empirical example. So I took baseline measures of a longitudinal study. So this was a study done by, I think, Greg and Marissa. And Marissa, maybe you can help me if I have questions about some of the variables along the way. There are 293 providers that are nested in 59 different clinics. So for our multi-level study, we're going to have a level 1, which is a provider level, and level 2 will be our clinic level. And we can talk about levels and what those are when we get to multi-level modeling. But for those of you that are familiar, that's the general structure of the data. I'm going to use three general measures. So one would just be norms. So these are norms at the provider level, norms of sort of the organization. I'm going to have openness towards evidence-based practice. So at the individual level, how open are you to trying new practices in your workplace? And then we have intentions, which is intentions to use evidence-based treatments. Does that seem good enough, Marissa, or do you think we need to go into any more detail, or are people okay with norms, openness, and just intentions? And we can move through that. Awesome. Okay, well, let me know if you have questions. I'll do my best to answer them, and if not, I will ask Marissa to help me. So in general, those are the data that we're going to use. So let me start by reviewing mediation. I do want to say for these measures, they were all measured at level 1. So we have a measure of norms, openness, and intentions at the provider level. And then, of course, providers are nested in different clinics. All right, good old media.
I was going to say one thing, and so now I'm sort of tempted even more to say it. So norms. Okay. So yes, these are individual providers that are providing ratings on all of these variables. Norms is about the clinic. So how do members within this clinic behave with regard to implementation? Is it a norm for people in this clinic to go above and beyond to help with implementation?
Got it. Yeah, so it's an individual level report, but they're reporting on what they think happens at the clinic level. Yeah. So I would say it's measured at level 1, but it's in reference to what they think is happening at level 2. Yeah. All right. So let's talk a little bit about mediation. All right. So in general, I like to view this as a concept, right? So mediation is a concept. The idea is that the effect of one variable on another passes through a mediator, right? So if you have some variable, it could be anything, we'll call it X. There's some effect of X on Y, and the effect of that is going to pass through a mediator. A more detailed or nuanced version of this is that the total effect of variable X on Y may be separated into a part that's a direct effect. So we can take some sort of total effect of X onto Y and separate it into two parts. One that is direct, which goes directly from X to Y, and another part is indirect, which is going to go from X to M and then from M to Y. And I guess I should back up. The reason why I like starting with this is just as a concept is because this is what our theories state, right? So when we're doing implementation science, we could have a theory about the relation or the effect of one variable on another, and we could believe or hypothesize that the effect of one variable on another is actually passing through some mediator. And so when we're thinking of implementation strategies, we can try to intervene on X or on M. And if the outcome that we're trying to affect is Y, we might actually intervene on X or M in order to get the effect that we're looking for on Y, right? So we're going to start with that as a concept, because when we're describing our studies and when we're trying to decide on what to intervene on or whom to intervene on, right, it can be at any of these points, knowing that the effect should carry over all the way through Y. And that is what we want to look for. Now, I'm going to come at it from a statistical angle, right? So if the theory states that mediation exists, we want to take the measures that we have, like X, Y, and M, and we want to test whether or not we have support for that theory. So what we'll do is we'll perform some sort of analysis that allows us to test this concept, right? But I think it's important to start there, that it really is just a concept, and then we'll collect data and we'll see if the concept matches our theory, or we have evidence to suggest for our theory that mediation exists the way we expect it to happen. So let's decompose this a little bit, right? So we have this total effect, and then we have this indirect effect and a direct effect, right? So the way I like to think about it conceptually is that you have some variable X and some outcome variable Y, and normally we have what's called the total effect, which is usually labeled as C, and at least in the mediation literature. And the way that I'll sort of present this, I think I'll do this on just the next slide itself, but the way that we'll present this is that this is just going to be like a regular regression analysis. So I'm going to use X in a simple regression to predict Y. The total effect was just the expected change in Y for each 1 unit increase in X. But really what this is what is the effect of X on Y while ignoring everything else that's out there, and also sort of assuming that there's no other effect out there, right? So just regular basic regression of using X to predict Y, and that's my total effect. And then a second model, right, where I'm including the mediator. What we have here is actually just 2 regression analyses, right? So I have an outcome variable Y, and there's 2 predictors in that one. So I have M predicting Y and X predicting Y. And then a second separate regression analysis I have M over here as an outcome and just X predicting M. And what happens is I'm getting estimates A, B, and we call this C prime. And the indirect effect of X on Y that goes through M is going to go through A and then B. And now the direct effect is the C prime here. And the really cool thing about this methodology is that this total effect, right, the C that we get over here when we use just X to predict Y, it can literally be decomposed into these two parts. So you have A times B plus C prime will always exactly equal C over here, right? So what we can see is that this direct effect that we're getting from this analysis and this indirect effect, which in this case is A times B, if we added those two things together, we would get C from this analysis. So it's really a direct match of the concept that we initially start with and then the analysis that we'll do with those variables. Right, and I think I just try to break this down a little bit further. Let's focus on just this one for just a moment, right? So in this one, for just a moment, you can see that this is just a regular regression analysis where we have some intercept and a slope, right? So X is predicting Y in this regression analysis. This is just the residual, right? So this C is that slope here. And I added this one just to be a little more complete, although it's probably unnecessary, but there isn't anything predicting X. So it's just an intercept only model. It just has its own little intercept there and there's nothing else predicting X. But if we were to translate this one into regression analyses, we would have two equations, right? So we have one with Y, and it's being simultaneously predicted by, I should have had missing one, should be a B times M in there. And then we have a C prime times X. Okay, and then this M is being predicted by X. And one of the things I would like to highlight is that it really is just those regression analyses. So if you do this as structural equation models or you do this as regression analyses, you'll actually get literally the exact same point estimates. The standard errors will differ in a very slight and trivial manner, but otherwise everything generalizes, right? So all we're doing is, in this case, we're fitting two separate regression analyses where Y is being predicted by both M and X, and then M is being predicted by X, right? Two separate regression analyses for that. And for this one, we just have Y being predicted by X. Right, and so really by doing these two side by side, we're actually decomposing this effect, this total effect of C into two parts, one that goes through the mediator and one that goes directly from the predictor to the outcome. All right, so for our data, to be able to do this, I'm going to look at the clinic level. So what I'm going to do, remember I said we had 59 clinics and the providers are nested in those clinics. So what I've done is I've just taken each of the providers in a given clinic and I've averaged across those providers. So every single clinic will have one measure of norms, one measure of openness, and one measure of intentions. And so I'm going to have sort of 59 rows of data, one for each clinic. And then for each clinic, I have a measure of norms, openness, and intentions. And so what I've done, right, so by performing the analysis, right, you see that you get, if I'm choosing norms to be my predictor, choosing intentions to be my outcome, you know, we can say for every 1 unit increase in norms, I expect a 0.5 change in intentions, sort of a significant effect there. That's great. But if I wanted to assume that the association between norms and intentions is mediated by openness, and I fit this model, right, then I'm going to get estimates of A, B, and C prime, right, A, B, and C prime. And I can form the product of A times B, can also test its significance. And then I can take C prime and add an AB, and you'll see that this C prime plus AB is equal to exactly the original C estimate that I have here. So what I'm doing conceptually by performing this analysis is I'm saying, okay, if I do think that there's some effect of X on Y, can I account for some of that effect through some mediator? Okay, not only will this estimate be identical across the two models, right, but its standard error, its p-value will also be identical. So it's really just taking that C and it's decomposing it into two parts. One that's a direct effect. So part of this 0.5 is here. It's 0.317 is the direct effect going from here to here. And part of it is going through the mediator M. That's the 0.183, just like that. Okay, so again, mediation is a concept. It's just the total effect of one variable on another. It passes through a third variable. Importantly, causality is assumed. I don't really want to dive too deep on this. Mediation gets a pretty bad rep in the literature. I'm sure you're aware of that. People always say you can't feed mediation models and assume causality. That's obviously true. that's also true of any statistical model. So if you're worried about ANOVAs, for example, ANOVAs are also not assuming causality, so you can't infer causation from that. That's based on the experimental design that you have. Regression analyses, multi-level models, structural equation models, it's all the case. So of course, in this example, norms, openness, intentions, I have to have some theory that hypothesizes that norms are causing norms are causing openness, which in turn are causing intentions. Maybe my theory does prescribe that, and that makes sense. But of course, I can't assume causality just like I can for any other statistical model, unless I really think that that's what's happening, right? But that's not to say that these models aren't useful. I think they're still useful. They just have that limitation. But of course, that's not different than any other model. So I wouldn't get caught on dying of the hill that we can't use this because I can't assume a causal direction of these things. I think you just have to be mindful and thoughtful about how you apply them, and then also be mindful and thoughtful about your corresponding interpretations. Seem okay? People have questions about mediation before we move on to MLM, what it is or anything like that? All right. So let's talk a little bit about multi-level modeling. Right, so multi-level modeling is a statistical framework, right? In general, the framework was developed to be able to account for dependence. So in our classic regression models and ANOVA models, we get to capitalize on an assumption that every single observation that we have is independent from every single other observation. So the idea would be, like, if I have rows of data, if I go back to the clinic example where I have one clinic and then another clinic and another clinic, the idea would be that each clinic is independent of every other clinic, right? So one clinic is high or low on a certain variable, I can assume that it doesn't mean that the next one's going to be high or low, or so on and so forth. This doesn't apply to all data collected, right? So for multi-level data, the idea is that the data can be grouped according to a specific structure, and that we don't really want to assume that people from the same group are independent, right? So in our empirical example, we have 293 providers, and they're nested into 59 different clinics, okay? And so one way to treat these data, so if I wanted to use just a regular regression and ignore the grouping, in a regular regression, I could have 293 rows of data, one for each person. And then I could use X to predict Y in like a regression analysis using those 293 data points or 293 rows of data. The regression analysis, based on the way it calculates standard errors and p-values and things like that, that regression analysis is going to assume that each row of the data is independent of every other row. But that might not be the case for this type of data, right? If you have 293 providers that are each in 59 different clinics, it's possible that people in the same clinic are related to each other. And by related, we just mean that, you know, for example, like the norms, if people are rating what the norms are like in their clinic, then people from the same clinic are probably going to have a similar measure for the norms because they're in the same clinic, right? Like that makes sense. So in the regression world, we would assume that every single person is, and the responses are independent. They're not related to each other. On the other hand, in a multi-level modeling world, right, where we have multi-level data, there's grouping structure exists, and we no longer want to make the assumption that the data themselves are row by row independent. So instead we're saying, like, well, if you're in the same clinic as someone else, maybe the answer to this questionnaire is going to be similar to those people, right? A different way of thinking about it is, if I know one person in one clinic and I know what their score is, I can probably guess or have a good guess what the next person's score will be in the same clinic because they're from the same clinic, right? And so in this case, we want to be able to have a statistical framework that can account for that. And that is exactly what multi-level modeling is trying to do. It's trying to account for that dependence because we can't assume that it's not there. And so then we have to sort of adjust p-values, standard errors, and confidence intervals to be able to account for this type of dependence existing. Right, so one way to think about this conceptually is if I'm looking at the association between norms and intentions, let's say I'm just looking at 3 clinics, maybe the data from this clinic sort of look like this, right? Some type of positive association between norms and intentions. But there's a group over here, right? This is a group of people, and their average on norms is a little bit lower, and their average on intentions is a little bit lower. So people who sort of fall in this clinic, like, are going to cluster around that average, right? So they have some sort of dependence or association. Norms is, this clinic is the same way, right? So there's some sort of link between these people. That's why they're all clustered together. and for this clinic up here, right? And we have 59, so I didn't draw 59 lines, but we can imagine like 59 lines could easily exist. Now, how we're going to handle this with multi-level modeling, I think I'm gonna get this, right? What we end up doing is we give every single clinic its own model. We give each clinic its own intercept and its own slope, right? So if I'm imagining the association between norms and intentions, right, it makes sense that this group or this clinic gets its own intercept and slope for the association between norms and intentions, right? And then this group, they get their own intercept and their own slope. And this one, they get their own intercept and their own slope, right? And the idea is that the residuals, right? So the part of the data that's left over after I account for that slope, that those are independent, right? And so that's how we kind of get around the assumption of dependence, is by giving each group its own intercept and its own slope. I'm going to assume that the actual residuals are independent and calculate standard errors and p-values based on that independence assumption. Whether or not that's true is a totally different story, by the way. We'll talk about that later. Right, so in general, what we have is we're going to say, let there be G groups. So in our case, we have 59 clinics. So our capital G here is going to be 59. And groups are labeled with a lowercase g, which goes from 1, 2, 3 all the way to G. So we would go from 1, 2, 3 all the way to 59, you know, clinic 1, clinic 2, clinic 3, all the way to 59. And the general model is written like this, right? So I have some outcome variable. This could have been intentions for individual I in group G. And then we have an intercept for group G, right? So an intercept for one of the clinics, and then a slope for one of the clinics, right? So the association between norms and intentions is going to have a clinic-specific intercept and a clinic-specific slope. Right? So the one way I sort of like to think about it conceptually is that, you know, we have this model, right? So X predicting Y is happening for every single clinic, and I've added a 1 to all the way to the G of the clinic, and then I should have put down here a capital G, right? So I literally just have the same regression model over and over and over again, right? And I'm going to get a bunch of intercepts and a bunch of slopes, right? I get one intercept for every single group, and I get one slope for every single group. Okay. And so it's sort of like saying, if I separated the data out into different groups, I could estimate each intercept separately, and I could estimate each slope separately. Instead of doing that literally, although conceptually this is what it's doing, what we're going to do is we're going to assume that those intercepts and those slopes, they follow a multivariate normal distribution. And this is really nice, right? So like, imagine I have 59 clinics. If I had 59 intercepts and I have 59 slopes, and someone said, okay, like, what's the association between norms and intentions? You really wouldn't want to go point by point and say, well, the association for this clinic is this intercept and the slope, and the association for that clinic is that intercept and slope, and so on and so forth. Instead, a more parsimonious way of describing it is saying, well, the average intercept is this value, and the average slope is this value, right? So you're going to get an average slope across the clinics, and then you're also going to get some variability around those slopes, right? So how much does that vary from clinic to clinic? And so instead of estimating these intercepts and slopes exactly, we're actually going to obtain an average for each of the intercepts and slopes, a variance for the intercepts, a variance for the slopes, and a covariance, right? So what we hope is that in the population, right? So instead of just my 59 clinics, the hope is that in the population, I can talk about these averages and variances around them, right? So I'm getting sort of deviations above and below those averages for different clinics. And here's the key assumption. So the assumption, in case you're interested in the distributional assumptions, right? But the key here is that these are residuals for each individual in each clinic, right? So after I account for a clinic-specific intercept and slope, I have a part that's left over. We assume that the part that's left over follows a normal distribution, and that has exactly the same variance across all the clinics. And this assumption is basically saying, once I've accounted for the group-specific intercept and the group-specific slope, now I just have that regular residual variance like I did in regular regression analysis. And so everything's independent. Again, whether or not that's true is sort of a different story. Now, what you may have seen before is that this can be written out in a slightly different way. So I still have this equation, or I have an individual I in group G or clinic G. I have a group-specific intercept, a group-specific slope. Okay, but what I can do is I can take these intercepts and slopes, and I can place them at what we call a level 2. And now what I'm going to do is I'm going to give the intercepts their own regression equation, and I'm going to give their slopes their own regression equation. So in this case, I'm not actually predicting them. Instead, I'm just estimating what we call a fixed effect, right? So this gamma 0, 0, this is going to just be the average across all the intercepts. And then this U0G is a deviation above or below that. And this gamma 1, 0 is the average across all the slopes. And so what we end up assuming is that this B0G, B1G, that follows normal distribution. Instead of having the mu's here, like I had before, I'm putting in the gammas because that's what my averages will be. And then instead of having the u's here, these are just going to be the variances of the u's. So this whole model that you may be more familiar with is identical to this one. They're exactly the same. But the benefit is that if I really wanted to, I could predict these intercepts and slopes. So maybe certain groups or maybe clinics that have a higher slope, right, or a higher intercept, maybe I can use a variable at the clinic level, like number of people that attend the clinic, or maybe sort of some implementation strategy that's randomly assigned to different clinics. I can use that to predict those intercepts and slopes. And that's sort of the buy-in or the benefit of the multi-level model. All right, so what's the concept of multi-level modeling? Well, our data, they have some sort of dependence, and that's because people are grouped in a certain way. So like in our example, people are grouped into different clinics. And so we can't assume that the measures that we have are completely independent. That makes it really hard to estimate standard errors and p-values and things like that. But if we assume that the residuals are independent after modeling the grouping structure, which is to say, if I give every single group its own intercept and its own slope, and then I collect the residuals, I'm going to assume now that those residuals are independent. And then it's actually pretty easy to figure out what the standard errors and the p-values should be, because it's essentially a distilled version of what we do in regression. So in practice, right, we're going to estimate separate intercepts and slopes for each group. We're going to assume that those intercepts and the slopes follow multivariate normal. We assume the residuals follow a normal distribution with the same variance across groups, and we assume that the residuals are independent. And we say yay assumptions, because those may or may not hold in any case, right? But in general, this is the buy-in, right? So when someone asks you, why should you use multi-level modeling? People's typical response is, well, I have hierarchical data. And the answer is actually the only reason why we do it is because we have a norm in our field that if we make all of these assumptions, everything's okay. And whether or not everything is actually okay is a different question, right? But you should just be aware that that's actually what's going on. I will say one of the nice things and what I really like is that I think conceptually it's very nice to have these sort of the average of all the intercepts and slopes and variance around that, right? Because this is what should generalize. You don't really care about an intercept and a slope at a clinic level. You want to know on average, what does this look like across all the clinics? And how can we test if certain clinics have higher or lower intercepts and slopes? So if I had used our empirical example to estimate this model, or I had norms at the individual level predicting intentions at the individual level, I would have gotten this value. And what I like, this is sort of like my average intercept. So for a situation in which norms was 0, we would expect intentions to be on average across all the clinics 3.757. And then on average across all the clinics, the slope should be about 0.525. And in most cases, researchers are just focusing on those fixed effects, the averages across all the intercepts and slopes. Seems okay? Do you have questions about it so far?
So I had a quick question, John, about the assumptions. So I guess 2 questions. How robust are these approaches to departures from normality, both for the variables and the error terms? And second, how in depth do you go in kind of reporting that when you're publishing on this?
Yeah. So okay. So in general, the answer always is it depends on how far away from normal the data are. In this case, it depends on how far away from normal the residuals are. Let's say you have a distribution that looks relatively symmetric. So let's say you have like a 1 to 7 scale where the average is like 5.5, and there's a little bit of like negative skew, you know, so like some people are down at the tail, but not that many, but it looks kind of bell-shaped, you know, pretty robust. You would expect these results to be great, and it would generalize up, and chances are if you replicated the study, you would likely find things within range. Let's say on the other hand, you have a huge ceiling effect. So on a scale of 1 to 7, 50% of people have a 7. 30% have a 6, and then it really tails off and virtually no one has a 1 or 2, 3. Not so robust. You're going to get actually a hugely inflated sense of power and a really biased estimate. So the answer is always the degree to which it deviates from normality is the degree to which the assumptions won't hold. And it's really difficult to say exactly what that degree will be unless you can, I don't know, do a simulation and study it directly. Now, for me, when I work on it, I would rather not make the normality assumption if I don't have to. So the degree to which I'll test that is I actually will grab all the residuals and then run some tests to see if things aren't normal. If things are pretty far from normal, then I'm going to try to do some sort of bootstrapping if I can. And if I can't, then I'm just going to be really, really cautious about the results. So the other way of dealing with it would be to try to model the data in a more direct manner. So for example, if I have that ordinal scale, I can try to treat the data as ordinal, but then whether or not that model is going to run is sort of a different story. So I'll probably do what I can with what I have in the sense of like, yeah, let me run the analysis. Let me assume everything is normal. Let me do some tests to see how far away it is from normal. If it looks pretty bad, then I'm going to try to do some bootstrapping or alternative methods that don't require the normality assumption. And then I'm going to check to see how far away the results are for the original analysis that assumed normality versus the one that doesn't, and see if they're night and day different. Kind of like, I guess, a sensitivity analysis. But things can be pretty far off for sure, depending on which way you look at it. Yeah. Other questions that people have?
I have a question about the norms on sample sizes within each of these levels.
Good question.
In this case, I'm assuming you're going to have different numbers of providers at different clinics. So,
Totally.
Yeah, what are there? Is it more a norm-based approach or kind of a power analysis approach on figuring out how many you need?
It's both, and it really depends on what you want to look at. So there's two sample sizes, right? There's the number of people that you have per clinic, and then there's like the total number of clinics, right? In general, the fixed effects, right? So like these gammas are more a function of the total sample size you have, which is, in this case, it would be the total number of people, that 293. But the variances of these effects, right? So these variances, which are the variances of the random effects, they're more a function of the number of clinics that you have, the number of level 2 units, right? So we have 59 clinics. And this makes sense, right? Because this is trying to say, hey, this is the variance of the intercepts, and this is the variance of the slopes. So am I able to detect variance of intercepts and slopes is actually more a function of how many clinics do you have rather than how many people you have in the clinics. So yeah, the answer is something along the lines of, and this is not a great answer, but it's always more is better, right? Like you want more people and you want to have more clinics. Obviously, there's going to be some sort of ceiling on that effect. But the estimates themselves of the fixed effects are usually a function of the total sample size you have, whereas the actual estimates of these variances and covariances are more a function of the total number of level 2 units, or the number of clinics that you'll have. So you try to aim for as many as you can for both. You could do some sort of power analysis, and I have done that before, although I don't recommend it. You could do some sort of power analysis to figure out how many you need to try to detect those. But I think that to whatever extent you can, you're going to be limited by the study itself. Like, I think the truth is, in this world, we're not doing a power analysis and saying like, okay, I need 50 people per clinic and I need 60 clinics and then we're good to go. We're just scrambling to get as much data as we can, and we're throwing the Hail Mary and hoping that we have enough to detect effects. I think that's typically the way it plays out, knowing that in the back of our minds, more is always going to be better. Yeah, it's probably not the answer we want to hear. It's also, I think, the boat that we're in. Yeah.
I guess a question, what's the minimum number you would feel comfortable with at level 1, just in order to be taking an average at all to get...
Yeah. Well, in this one, I had somewhere between 1 and 11 people per clinic, and most of them were somewhere between 1 and 5. It's a really good question. Like, it's exactly what we should be asking ourselves. Like, well, how much information, how much data do I need before I'm going to draw conclusions? I would always say, if I were to really want to trust the results, let's assume for a second that I have good, reliable measures. Yeah. So if I really think that the measure of norms is a good one and the measure of attentions is a good one, I would probably say at least 20 per group, and probably closer to 50 is better. And the same thing, at least 20 clinics and probably closer to 50. But honestly, that's not based on anything more than intuition, right? So like, I don't really know if that answer has a lot of merit. And it's also assuming I have good measures of these things, right? I think a different way would be that I think about that question is, what's the minimum number of people I need to see within a clinic, and how many clinics do I need to see before I think these results will generalize, right? And I think the answer to that question is more dependent on how much do you trust that these measures are going to give you good insights into what is going on at the clinic level, right? So for example, if there are only 10 people in the clinic and I really think I only need to measure 3 people to get a really good sense of the norms, then maybe it's just 3 people, right? But if I have a clinic where there's 100 people and I'm trying to think of a measure that might vary a lot more from person to person, then I might need 20 or 30 people before I have a good measure of that. So I think it's much more of like, I can't give one answer that's going to be true across all examples. It's more about like, well, at what point do I think that the average that I'm getting across individuals within a clinic is actually going to be a good representative of that average? And that will depend on the clinic, its size, and how good the measure is. Yeah. But I'll answer the question a slightly different way. I think it's going to be hard to publish on something where you have less than 20 people per group, and it will be hard to publish on having less than 10 groups. Nothing's impossible, but maybe set that as like a lower bound. Yeah. And that's just sort of practical constraints. But there's no perfect answer to that question. It will depend on what you're studying and how much you trust the measures and how large those groups are, like in general in the population.
An additional consideration that we've often included was within group agreement. So we might run some stats to look at agreement between individuals within a clinic and see, well, is this actually a clinic level construct? Is this group sort of responding like a clinic, like a unit? Or John, you mentioned a clinic with 100 individuals. Might they answer cohesively? Not sure.
Yeah.
So that's something that we often consider as well. In addition to the number of members, what is the agreement like between those members?
Yeah, for sure. Hopefully it's high, and hopefully you haven't just accidentally sampled the 5 people who have the same answer. But yeah, that's always the consideration. Other questions before we keep going? All right, so yeah, so each group has its own intercept and its own slope, right? So these were going to represent averages across intercepts, averages across slopes. Oh, and I do want to mention this. So eventually when we get to multi-level mediation, we're going to go back to our path diagrams, right? And remember when we had a path diagram, we just had X and then an arrow to Y, and we said that was represented by a regression analysis. When we have these path diagrams for multiple mediation, typically what we're going to do is we're going to have a circle here. Circles in general represent latent variables. Latent variables are variables that are not in your data set, right? So they're things you didn't measure. So this is something that does vary. And this is also something that's going to vary. This slope here has a circle here because it's going to vary, and it's going to vary for different groups, right? So different clinics are going to have different slopes. And I'm going to summarize that with a mean and a variance. And what I'm going to do is I'm going to say this circle can be here, right, at level 2. This is the clinic level. Okay, so actually it's like this circle is actually supposed to be the same as this circle, right? And this circle usually is represented by the random intercept, right, which also gets placed over here. So if you see like the M+ manual, for example, you might see diagrams like this, where once you have a level 1 variable, individual I in group G, And the level 2 variables are varying across groups, just group G. And then there's an intercept for each group and a slope for each group. So we sort of see them briefly at level 1, but we're actually going to model them at level 2. Yeah. These diagrams are super, super confusing. If you don't like them, then you're right where you should be. All right. And just to give a great lead in, I've lied to you entirely about multi-level modeling because we need to talk about centering. This is super important. All right. So centering is of the utmost importance in multi-level models, and we haven't even talked about it. And I already analyzed the data with multi-level models and interpreted results. So it was not good of me, but I wanted to at least have something about centering, or at least something about multi-level models in your mind before we started talking about centering. So this is sort of also a higher level concept. If we're looking at the association between two level 1 variables, there's actually two distinct ways that they can be related, right? So remember, we're looking at norms versus intentions, right? And we have associations, in this case, with 3 different clinics. What I want to do here is I want to draw the means of each of the groups. So the circles represent the averages. And what's really nice is that for a given clinic, right? So for this clinic here, the average for norms, right? You can see that, let's say all the data fall along this line. Okay, that if I wanted to know where the average of norms was, it would just be the average across the line in this direction, right? Which will be right here in the middle of the line. So the average of norms for this first group should occur right here. But then the average of intentions, right, will be the average in this small vertical direction that spans the line. And so the average for this one will be right here. Okay, so where the average occurs on the predictor is also where the average occurs on the outcome. And it doesn't matter, they don't have to perfectly fall on the line for this to happen. If all the dots are scattered around this line, and this is the regression line that best fits that clinic, then these averages will occur in the same place. Okay, so that's true. So I have an average here for this clinic, I have an average here for this clinic, and an average here for this clinic. Okay. Now what I'm going to do is I'm going to separate out that original plot into 2 separate plots. So I'm just going to take the averages, and I'm going to move them over here onto this plot. So this plot and the X and Y axis should be the exact same as this one, but I'm looking at the averages. Yeah. Okay. And what I've done over here is I'm going to create a new variable called X star IG. This is the same as my original X variable. So this is norms for individual I in group G, but I'm going to subtract out the group mean for each person. Okay. I'm going to subtract that out. So what does that look like? You know, let's say this scale goes from like 1 to 10. Yeah. And let's say this means right here at 2 for this group. So for every single person, I'm going to subtract out a 2, and that's what their mean is. And what would that look like if this goes from 1 to 10, and this, let's say 0 is like right here? It's kind of like I'm picking up this line, right at the center. I'm picking the whole line up and I'm moving it down and dropping it right at 0, right? Because now the mean of this will be 0, right? These people will be negative, they're below 2. These people will be positive, they're above 3. I'm just moving that right here, yeah? And then the same thing for this line. If I subtract out this group's mean, it's like I'm picking up this line and moving it right down to 0 too. So the means for both of them are going to line up at 0 now. And the same thing for this green one, just moving it all the way over. So you see that those 3 lines, if I pick them all up and stack them all on top of 0, because I'm subtracting them, they should all be stacked above and below one another, right? And that's exactly what this plot is here. So if the means here, they're all stacked around 0, yeah, it's kind of like wherever this 0 is, that's where 0 is here. And now I have the within group part. So there's a mean of 0 for everything, and then people are just above and below their own group mean. Okay. Now, when we did multi-level modeling before, on the example just before, I used this variable to predict this variable. And every single group had its own intercept and its own slope. But because I have one slope, there are 2 pieces of information that are being summarized by that. I'm summarizing the association between the means, you see the means of norms and the means of attention, and the within group effect. Okay, so imagine each group has its own slope, right? There's an average slope across these. Okay, that's one source. We usually call that the within effect. It's the average of these slopes. And the between effect, we usually look at this line here, which is asking the question, for a 1 unit increase in the average, how much does average intentions change? Okay, these are 2 separate pieces of information. So variables can be related based on their averages, right? And they can be based on deviations above and below averages. And this association can be different across groups. This is one association across all the groups, right? Because I just have 1 point for each group, right? Now, when I analyze the data this way, by using the original variable for norms, predicting the original variable for intentions, the slope that I get is an average of this and the average across all these. Okay, so in this case, maybe not the biggest deal because this is positive, and maybe the average of this is also positive, but there are many problems in which this happens, right? So for example, if the data happen to look like this, there's a positive association among these means, but a negative association within the groups. So if you were to analyze data that look like this with a multi-level model and not center, you probably would get an effect that was 0 because the positive effect would average out the negative effect. Okay, and same thing over here. The means have a negative association, but within each group, the slopes have a positive association. So if you were to do the original way that we analyze the data and not center, the effect, again, would also be something close to 0 because it's taking a weighted average of this negative effect and the average of these positive effects. So what we want to do is separate that into 2 parts. Right, so what we do is we're going to extract out the group mean from the original variable, and we're going to use that at level 1. And then what we can do is we can use that group mean as a separate predictor. And I think I do that right here. I can use that as a separate predictor, right? And remember what I said, wherever this location occurs for the group, then the other variable, that will also be where the mean is on Y. So this association, this gamma 0, 1 here, is going to be the association between the means, right? This is the mean of X, and then it'll eventually be the mean of Y. And this B1G, this is a group-specific slope. Okay, it's a group-specific slope, and so this gamma 1, 0 will be the average across all those. So this is commonly referred to the between effect, and then we have this within effect here. So the way that I like to think about it is that one of the effects I'm getting is how are the means related, right? Which is really talking about the clinic level, right? How is the average a response of an average norm at a clinic related to the average intention, just at the clinic level? And norms, right, and intentions, this is at the individual level. So for individuals who are above or below their own mean, what is the association with intentions and the individuals at the clinic level, right? These are 2 separate things. This is asking the question, what's happening at the level of the clinic, averaging across them. And this is asking, what's the effect within a clinic and what is the average across them? Let's see, the question is, we are coming up on 3 p.m. When are we slated to finish? Soon. I think people can come and go as quickly as they want. Let me jump to this. When we originally analyzed the data, right, we got an average intercept and an average slope, but what we didn't do is decompose this into 2 parts. A part that is due to the between effect, the averages across the clinics, and a part that's within. And you can see that when I analyze the data a separate way, where I'm actually having separate parts, one for the averages and one for within the clinics, right? I get 2 separate estimates that are both significant and positive. And you can see that this one gets pulled more towards this value because it's a weighted average of these 2 things. But what I would be doing is I'd be taking this effect and decomposing it into 2 parts. And importantly, what you might find is that one of these is positive and the other one is 0, or one of these is positive and one of these is negative. And you're asking different questions because you're talking about what's happening at the individual level versus the clinic level. We really are coming up on 3. Can I just do one quick one to get to actually what we intended to talk about today?
Yeah, go ahead, John.
Okay. So when we combine this, right, when we combine this, what will end up happening is we're going to have measures of individuals in different clinics, and we can have them for our X variable, our M variable, and our Y variable. And what I always recommend is let's split it into 2 parts. You can take the averages of people within each of the groups and you can model those. And guess what? This is exactly the same as the regular mediation we had just done before. And then you can look at individual level associations between X, M, and Y. And these associations, they can vary across clinics, and we'll get them as separate variables that we can analyze over here if we want. Right, so it's the separation of the between and the within part that's the most important. And then we get that separation by looking at these averages for level 2, and then keeping our group mean centered variables at level 1, and then modeling those differences. And so when I do this, I'll just do this one side by side. This was the analysis where I did a multi-level mediation. And this was the original mediation analysis. And you can see that the A, B, C prime, and AB effects, that those are essentially mirrored across the analyses. But what I'm getting on top of it, in case I'm interested, is these are effects that are happening at the individual level. And what we see is that I don't really have an association between X and M for individual levels after this has been accounted for at level 2. So the only reason that those are associated with one another, X and M, which would have been this B effect here, is because it's happening at the clinic level, right? So there's a clinic level association between norms and openness, but that's no longer occurring at the individual level once those means are accounted for. But I am still getting associations between M and Y and M at the individual level above and beyond what I'm getting at the clinic level. Now, the last sort of pieces that you can do, and we're going to just touch on this real quickly, is now that those things are variables that we can model, you can also use group level averages to predict them, right? So if I wanted to look at how the association at the individual level is occurring between norms and openness, I can ask clinics with higher norms of people sort of doing what they're supposed to do those clinics tend to have a stronger association between norms and openness at the individual level, right? It's allowing me to examine those types of relations. I didn't explore that here, but we can do that. Okay. I don't want to take too much time. The last piece I'll just say in one sentence is you're probably going to want to use Bayesian estimation to do this. Now, I'm happy to stay for another 10, 15, however so many minutes, because I know I had to get through a lot. So let me know if you have questions, and then we can sort of jump back to anything you want, while recognizing if you want to take off because you have other things you got to do today, but that's okay too. And sorry, I didn't leave more time for Q&A. If people have questions.
Yeah, you have a question in the chat from Amir.
So much. If I'm understanding correctly, multivariable linear mixed models, hierarchical model, multi-modeling, all the same concepts. That's true. So mixed models, hierarchical modeling, and multi-level modeling are all exactly the same. That is true. I'm wondering what differentiates a mediator from a moderator versus a moderated mediator and a mediated moderator. You can tell how much I'm confused. The way that this is drawn conceptually, so a mediator, I really think that the major difference is sort of how we assume causality. A mediator, I don't know why I feel compelled to go to the beginning of the slides, but for some reason I do. A mediator, I guess like a mediator occurs when the pattern is like this. So we assume that X is causing M and M is causing Y. Whereas a moderator assumes that there's some association. Let's say there's some association between X and Y, and there's some variable coming in that's changing the association between these two things. Let's say, for example, I don't know, reading, I don't know, let's just assume, I'm trying to think of an example that would be really easy, but let's say like the amount of study that you do versus how well you do on a test. You could have something like biological sex being a moderator. So there's an association between how much you study and how you do on a test, and males and females will have different associations between those two things, just like as maybe an example. But you probably wouldn't assume that the amount of study causes your biological sex, which in turn causes you to do better on the exam, right? Like that theoretically doesn't really make much sense. You might assume that your study time basically causes your knowledge of that study, and then your knowledge of that study should cause your test performance to go up, right? So it's really the causal chain that is really defining this as a mediator, versus a moderator here is basically shifting the association between these two, which is a slightly different concept. Yeah, so in a nutshell, that's sort of the distinction between the two. And I think the way that I always like to think about it is, well, do you think it's plausible that this causal chain exists, or do you think there's some variable that's affecting the association between these two? And usually you can differentiate between them. Yeah. And sometimes it's both, right? So like you can have a mediator coming in here, right? But maybe, for example, like, maybe like Greg and Marissa have this intervention, right? So maybe there's some intervention like that's out here that's moderating this association. So the intervention is coming in and strengthening this, and that eventually, like if A is more positive for those in the intervention condition, that's going to eventually lead to a higher downstream outcome, right? So that's another way that the maybe like an experimental condition can be a moderator, or you could just have it here, right, where this variable is assignment to an intervention condition. An intervention is going to cause you to do something more, like maybe engage in certain practices that are better for the company, and then that leads to better outcomes for that company, right? It can be construed either way, and it's more about how you want to construe the variable in this process. Did I answer the question, Amir? I think you're at least more or less, yeah. There's a really good book, 2017 by Andrew Hayes. I'll write it there. So Andrew Hayes, 2017, has a book called something like Causal Processes, something like I don't know, like mediation, moderation, and moderated mediation. I think something like that is in the title. And I think he usually uses the word called like process analysis, which gives a pretty good overview of it. Other people have questions or anything we want to chat about?
Vivian, you want to just ask your question?
Sure. Hi, Dr. Helm. Thank you so much. This was really, really helpful. I'm wondering, I know you didn't get a chance to cover it, but if you could give a brief explanation about why the Bayesian estimation is really important. I recently did a multi-level mediation, just my first time doing it. And some people did suggest that I use the Bayesian estimation, but my results didn't change. So I would love to hear why that's really important.
So, yeah, I'm actually really glad you asked this, because this is actually the part that I like talking about the most. So thank you for that. So the multi-level mediation is a really complex statistical model, right? So like I like saying this, the first paper that actually estimated that full model was in 2010, which is pretty recent, right? Like a lot of the stuff that we use, ANOVA regression, has been around since the 20s and 30s. So like this is pretty new stuff. The current example that I did doesn't run with ML. It basically kicked back an error that said, the way that I would translate the error that said, you're asking too much from the data. Like there's more than one answer that's correct based on the way that we quantify a correct answer in maximum likelihood estimation, and we can't tell you which one's the right answer. And if we think about it conceptually, like in my analysis, right, like if I'm trying to estimate this model that has these slopes that are allowed to differ across groups, it's going to be really hard for me to estimate how these slopes differ when some of my groups have just one or two people, right? Especially if I've mean centered this variable. So like, let's say I have two people in a group and I'm subtracting out the mean, I'm already pulling out a lot of information from those two people, and I'm still trying to get extra info, right? So it's really, really complex. And maximum likelihood is basically saying, okay, I have just the data. I'm going to search for the best set of parameter estimates given the data and the model you specified. But once we start to have a lot of parameters in this model, it just gets really, really hard for it to find an answer. And that's what it said to me. It said like, hey, John, I did my best and I didn't find an answer. And I said, okay, that's no problem. Now, Bayesian estimation, without going into a lot of detail about it, basically the mechanics of it, the model will estimate, right? So the model is especially in M+, the way that they designed that one, it's almost like a closed form solution. So the model will almost certainly estimate, and then you get to decide whether or not those estimates are reasonable. And the reason why I like that is because I fit this model, and then I fit a second model where these slopes were here, but they weren't allowed to differ across the groups, right? So the variance of these effects, I was like, let me just force them to 0. That one also ran. The difference in fit across the two approaches was essentially nil, right? So what that's telling me is like, I actually don't need these to vary across the different clinics. And of course that makes sense, right? Because I don't have a lot of people in each of the clinics, right? So it's going to be really hard to get that info. Does that info exist in reality? Probably, but I just don't have enough people per clinic to be able to estimate it, right? Maximum likelihood says, I can't do this whole model and I can't tell you why, Bayesian estimation, at least I'm going to get an answer, and then I can still compare it to other models where I force some of these parameters to 0, and I could still maybe drop some of these out. If you forced all these variances to 0 in ML, it does run, right? And that makes sense because now maximum likelihood has enough information to estimate that model. So that's great. But my question is always, okay, well, is it because the model was too complex that it couldn't run, or is it because the data aren't giving me enough info, or both? It's hard to know with maximum likelihood because I'm only getting one answer. At least in Bayes, I'm fitting this model that has those variances, I'm fitting another model that doesn't have them, and I can compare the fit and determine it, right? So it's just I always like to say, like, I'm not a Bayesian, really. I just know that this is the model I want to look at. And if Bayesian estimation is the way to get that answer, then I'm going to check it out as a plausible alternative, right? And so the answer is, like, you see this all the time, that the complex models, they just are really hard to estimate using classic ML approaches. But the Bayesian estimation doesn't have a problem with it because basically the math that underlies it, it can handle less information from the data. Yeah, and that's kind of the short version of it. Does that help? Do you have any follow-up questions about that, or?
Yeah, that's really helpful. I'm using the same data as you actually too, and I will probably do a multi-level mediation with that data. So I think I'll probably have more questions later on. But I was wondering if it sounds like you recommend this kind of just in general, but is there, I think this is again about the sample size issue, but if there were perhaps, like, 20, like you said, like 20 folks in a cluster, then is that a point where you might not consider doing that, or you would just test both and kind of see?
I would still, these days, I would probably just do Bayesian estimation and call it a day. Yeah.
Okay.
I think the space I land in on that one is I definitely trust the results from Bayesian estimation way more than ML. And I don't really want to wait. So, like, this model took 2 minutes to run in M+, which is honestly like amazing. The ML version, I think, ran for 10 minutes before saying I tried really hard and couldn't do it, which is fair, right? Because it's trying really hard for 10 minutes and then couldn't do it. So I think my patience is a factor. It probably shouldn't be, but the truth is, and it's exactly what you say, if both run, you should get basically the same answer as long as you're not incorporating strong priors into the Bayesian estimation, which I don't recommend. Like, I wouldn't recommend including really strong priors unless you really have good reason to include them. And so in that case, in my mind, it's like, well, I'm basically just using 2 different tools to get to the same endpoint. I'd rather just use the tool that I think is going to be more efficient, right? So, like, if I have a nail gun versus a hammer, I'd rather use the nail gun if I have to, put in 1,000 nails rather than going through and hammering them one at a time, because I think that the outcome is going to be the same, but the nail gun process is just going to be a lot easier. And I think that's kind of the way I view the Bayesian estimation in this approach. It's just a toolkit that allows me to estimate certain models, but it's going to happen faster and it's going to give me results that I trust because, at least in Bayesian, I can sort of say, like, okay, well, what happens if I drop out some of the random effects? What happens if I force the fixed effects to 0? I can estimate all those models. I can compare fit, right? With ML, you might not even be able to compare all the models, right? And one thing that I don't like is when people say, like, oh, this model didn't run in ML, so it's the wrong model for the data. And I'm like, no, it could still be the right model for the data. You don't really know what parts you should drop out and not drop out, right? Like, for example, do I need to drop out just this variance, just this variance, just this variance, all 3? Some people say, like, oh, well, it only ran in ML when I dropped out all 3. Maybe the answer is you just have to drop out 1. It's just really hard for that algorithm to work, right? So I think it's just a practical thing. Like, if the approach runs, then I would use that one. Yeah.
Thank you so much. That was really helpful.
Yeah, for sure. Other questions? All right. Well, sorry I ran over on time. But hopefully you found it to be useful and to be interesting. If you do have questions, feel free to reach out. I'm going to send the slides to Kira and she can share them with you all. And if you want, I can also share the M+ scripts that I use to do some of these analyses. And yeah, I think that's it for now. I'd share the data, but that's up to Greg and Marissa. No pressure.
Yeah, no pressure. Thank you so much, John. Yeah, this is super helpful and really nice and clear explanation and discussions. And yeah, thank you all for joining the seminar. If you're looking for continuing education units, we had that information in there, but if you have trouble, please reach out to us. And we look forward to seeing you at our future seminars and workshops.